Okay, so today we to be ready for the quiz on Wednesday, we will solve the quiz of last year. Okay? It was 2024. Okay, so the quiz will take place on Wednesday, 8:15 in the morning, I think, right?
Here?
No, in other classes. I don't remember the classes, but you should get a mail where to go. Okay, so the question goes like this. So we have a Gibbs potential of one-dimensional system of length L is G dependent on T and tau, where T is the temperature and tau is the tension. So that equals to we have T CL0 1 minus ln T divided by T0 minus S0 minus tau squared divided by 2bt minus tau Z0, where B, Z0, T0, C, and S0 are all constants, okay, and positive constants. So all of them are bigger than 0. Okay, so first we want to find the tension of the system as a function of the length of the system. And then we want what happened to the length when heated with constant tension. Okay, so first we want to find the tension of the system as function of the length. Okay, and then we want to see what happens to the system when we heat it up. Okay, so we have given the Gibbs energy of the system. Okay, we want to get to the tension of the system. So we need to pick up a thermodynamic equation related to Gibbs energy, okay, because this is what we're given in the question. And then from this equation we need to extract the tension.
Minimize equilibrium.
Okay, so we generally don't use this because we want to relate between two specific sizes. Okay, so what we do is we use the differential equation of the given energy we have. Okay, so the differential equation of the Gibbs energy.
Minus S dt minus L d tau.
Yes. So we have minus S dt minus L d tau. Okay, and we converted the pressure and the volume to the tension and the length with a minus sign. Okay, so this is the differential equation of the Gibbs energy. And now we want to extract the tension. Okay, so what we have here, sizes that are not sizes that are parameters in the equation are S and L, the entropy and the length. Okay, we don't have here the tension. So we have a little bit a small problem, but we see that we need to find the tension as a function of L. Okay, so we can extract L from this equation, find it as function of tau, and then extract tau from this equation. Okay, so we will find L using L equals to derivative of G relative to tau while t is constant. Okay, so dt will be equal to 0, and then this is correct. And from this we will extract tau. Okay, so derivative of g relative to tau while t is constant. So all these terms are just cancelled in the derivative, and we have two terms to derivative. So we have, this will be equal to okay, so we have the minus from the equation, and we have minus 2 tau divided by 2bt minus z0. Okay, so tau, from this equation now we can extract tau, and tau will be equal to bt times L minus z0. Okay, so we have the tension as function of the length, and now we want to see what happens to the length, to L, when the system is heated, when T is getting bigger. Okay, and we want to keep with constant tension. Okay, so if the tension is constant, okay, and T is getting bigger, so we're getting that we has to decrease this size. Okay, so when T is increased, L minus Z0 decreased. Okay, so when T increases, L goes to Z0. Right, so L is getting smaller. Now, this is not usual. If we think on a system of ideal gas. So what we expected in ideal gas when we
Expansion when heated.
right, when we're increasing the temperature, we're expecting that the gas will have bigger volume, right? The volume will be greater. So in ideal gas, when T is increased, V is getting bigger. The system is expanding. So the result we got here is the opposite from what we know from an ideal gas. Okay, this is a special result, and this is called what we get is called Joule-Thomson effect. So we have we got Joule effect. Okay, so this is a special effect that we get under in specific systems. Okay, so as we increase the temperature, the length goes to constant length. Okay, great. So this is the first section. Now we have, it is known that the constant B is B1 for some length that are smaller than some length L1, and equals to B2 for lengths that are bigger than this specific length L1. And now we're asked what have to be the relation between B1 and B2 for a phase transition. Okay, so we have two different behaviors for different lengths. Okay, so let's write the equation for the system. Okay, so the tension of the system will be equal to, okay, B1 tau L minus Z0 for lengths that are smaller than L1, okay, and it will be equal to the same but with B2 for lengths that are greater than L1. And now we want to find the relation between B1 and B2 so we could have a phase transition in the system. Okay, now the when it is written relation between B1 and B2, it means B1 is greater than B2, smaller or equal to B2. Okay. So let's draw the behavior of the two phases, okay, in all the possible relations. Okay, to see how the system behaves so we can decide what we need in the relation between B1 and B2 to get a phase transition. Okay. So we have the system with L as the x-axis and the tension as the y-axis as we draw the graph for V and P. Okay, same axis. And we have the L1 length where the phase transition occurs. Okay, let's start start with the easiest case where B1 equals to B2. Okay, so when B1 equals to B2, we'll just get the same line in phase A and in phase B. Okay, we just get a straight line that goes out from some point Z0 on the L axis. Okay, so we have this line. Okay, so for this case, the behavior is the same behavior. We don't have any unphysical area in the graph, so we don't have any phase transition yet. Okay, let's go to the case where B1 is bigger than B2. So when B1 is bigger than B2, so the slope of this graph will be sharper than the second one, so we will get something like this. Okay, big slope and the slope and more small slope. And the last case where B1 is smaller than B2. Okay, so we will get here more small slope than this phase. Okay, so we will have something like this. Okay, so those are all our possibilities. So we said that the blue possibility is we don't want it. We can't have here a phase transition. So let's look at the purple one now. Now, what we want in a phase transition, right? So we can have some jump in values of the system, but in a specific values, okay? In this system, we can have a jump in the length, okay? But the tension has to be continuous. So if we will take the purple graph, we can see here that we don't have any point that the tension is continuous between phase 1 and phase 2. Okay, there is no overlap in some values of the tension in phase 1 and phase 2, so we can draw some line of continuous tension to get a physical phase transition. Okay, so the purple graph is not physical, and we cannot do something to correct it. Okay, so we remain with the red graph. So in the red graph we have, let's take other color. Okay, so we have this area of the tension that are overlapped. Okay, so in any point in this area we can draw a straight line for continuous tension between phase 1 and phase 2 and get a physical phase transition. Okay, so only in the red graph we can have a phase transition. Okay, so here we need to get B1 is bigger than B2. Okay, now after we chose a system, now we can find the values for the phase transition. So the last section tells us that for the case we found in the last section, for B1 is bigger than B2, we want to find by using the Maxwell construction. So we want to find the critical tension and the length at the phase transition. Okay, so for some temperature, because our graphs depends on the temperature, okay, so for some temperature we want to find this equilibrium tension, okay, that goes from phase 1 to phase 2, and then we want to find the length of the phase transition, meaning the length in phase 1 and in phase 2, and we want to use the Maxwell construction. Okay, so what is the Maxwell construction? So in the van der Waals gas, right, we saw that we have, okay, this was our P and this is V, and we had, right, this graph. And we saw that the Maxwell construction says that the equilibrium pressure, when we draw a straight line of the equilibrium pressure, we get two areas between this line to the graph of the physical behavior, and those two areas need to be equal one to each other. Okay, so what will be the Maxwell construction in this case? Okay, so let's draw it again with only the relative relation between B1 and B2. Okay, so we have here the length and we have the tension. And this is our phase transition. And we had this physical behavior. Okay, now we want to find the equilibrium of the tension. Okay, and we draw a straight line in this value. Okay, should be a little bit lower. Let's say here. Okay, so we get two areas. Yes, so this is our graph, right? So we get two areas between the tau equilibrium line to the physical behavior. Okay, so we have this area and this area. And to find this this equilibrium tension, we need that those both areas will be equal one to each other. So what we need to do here is like in geometric way, to calculate this area, and demand that they will be equal. So let's see what are sizes here. Okay. So let's start with the top triangle. Let's call it A, and this will be B. Okay, so for A, we need the length of this line and the length of this line. Okay, so we know that this line will be equal to L1 minus the value of L in T equilibrium, okay, on the graph. So let's call it LA, where LA we receive from the first term of a phase A. Right?
Should I hit it too?
In a moment. Okay. The second line we want is the value of this tau, let's call it tau A, okay, minus the value of tau equilibrium. Okay, so what we have for phase A, right? We know that for phase A, tau equal to B1 T L minus Z0. Okay, so to find LA, we need to insert tau equilibrium in here, okay, and then we get the length LA, okay, for tau equilibrium. So we can write tau equilibrium equals to B1 T LA minus Z0, okay? So we get that LA equals to tau equilibrium divided by V1T plus Z0. Okay, now we want to find this tau A, this value where the equation of phase A gets reached to L1 value. Okay, so this tau A equals to B1T in the value of L1. Okay, now L1 is given, so we're okay to keep it, and tau equilibrium is what we want to find, so we're okay with keeping it. So for phase A, we get an equation the area of the triangle in phase A equals to multiplication of, so we have L1 minus LA, this term. Okay, so we have the equilibrium divided by B1T plus Z0 multiplied by the second line, so we have tau A minus tau equilibrium. So we have tau A, this size B1T L1 minus Z0 minus tau equilibrium and divided by 2. Wait, this is the triangle in phase A. Now we do the same for phase B. Okay, and we get that the size, the area in phase B equals 2, so we have here the half, and then we have tau equilibrium divided by B2t plus Z0 minus L1 times tau equilibrium minus B2t L1 minus Z0. Okay, so we have both areas, and now we need to compare between them. To say, okay, SA need to be equal to SB, and we want to find the tau equilibrium that satisfies this condition. So we want to take SA equals to SB. Okay. So what we have here, okay, the half and the half cancel the one with each other, so we have, let's see, okay, we have L1 B1 T L1 minus Z0 minus the equilibrium L1 minus C0 minus Z0 B1T L1 minus Z0, and then the second term with the equilibrium, so we have minus L1 the equilibrium plus tau equilibrium squared divided by B1 T plus Z0 tau equilibrium. This is for phase A. Okay, and for phase B, it equals almost the same. So we have the tau equilibrium squared divided by B2T plus Z0 tau equilibrium. What we have there, minus L1 tau equilibrium. And for the second term, so we have minus tau equilibrium L1 minus Z0 minus Z0 B2T L1 minus Z0, and the last term plus L1 B2T L1 minus Z0. Okay, what we can see.
Z0, tau equilibrium. The final
Yes,
term.
so this is cancelled with this,
Minus
and
L1.
this is cancelled with this,
And the minus L1.
right, and this is cancelled with this. Great, so actually all the terms that are without B1 or B2 are just the same in both phases and are cancelled. Okay, so we remain with, so let's gather terms. So we have tau squared, and we have 1 divided by B1t minus 1 divided by B2t equals to L1 minus Z0 times B2t L1 minus Z0 B2t plus Z0 B1T minus B1T L1. Okay, so what we need to do is to extract tau equilibrium, right, and see what we get. So we can write it a little bit more comfortable. So we have here, right, the L1 minus Z0 size, so we can see we have this size also here in the second term of the equation. So we can write it as L1 minus Z0 squared, and we remain here with
You can also take out the T.
right. So remain here with
B squared, sorry, B2 with plus
B2
B1
minus B1, right?
plus, I believe. No, yeah, minus.
Minus. Okay? This is equal to this. Okay.
But you can also,
Yes. To do the same for this one, right? So this is equals to 1 divided by B1 B2 T times B2 minus B1. Okay? So our tau equilibrium will be equal to square root of B1 times B2 T L1 minus Z0.
and I think there's supposed to be a minus. No, sorry.
Okay. Wait, this is really remind us the original equation of tau for both phases, but here we have a game between B1 and B2 constants. Okay, so we find our equilibrium, and now we want to find the length of both phases in the phase transition. So for this, we actually need to take our tension in both phases. Say, okay, this is equal to tau equilibrium, and then we extract from phase 1 and phase 2 the length. Okay, we want to extract this this length. Okay, so the equations are right, tau equals to BT L1 minus Z0. So we said, okay, for phase A, so we have tau equilibrium square root of B1 B2 times T. Sorry, this is just L, not L1. L minus Z0 equals to B1 T L minus Z0. Okay, and then we extract this length, okay, because we can do it. And the same we do for the second phase. So in the second phase, we have the same, but with B2. Okay, so we have B1, B2 times T. This will be LA. L1 minus Z0, that will be equal to B2 T LB minus Z0, and we extract LB from this equation. Okay. Questions? Any questions? Okay, so we'll see you on Wednesday morning on the quiz. Right, another message, next week is Hanukkah. So Monday is vacation in the university, so we won't have a lesson on Monday.
יש דרך נוספת למצוא למה יש שינוי חדש, שזה לא עם השטחים במקסוול, אלא בעזרת השיפוע של האנטרופיה, של מה היה השיפוע המחלטים.
אתה מדבר על האזור הלא פיזיקלי?
כן. באזור הלא פיזיקלי אפשר או להשוות בין השטחים, או לעשות השוואה בין השיפועים. שזה כאילו קשר של החוק הבסיסי בחטא או משהו.
נכון.
אז מה היה הגרף שעבורו אנחנו מוצאים את השיפוע?
כאילו למה פה השתמשנו דווקא במקסוול או...
לא, כאילו אם הייתי רוצה דווקא לא להשתמש במקסוול או להשוות שיפועים, אז פשוט לבדוק את זה ככה כזה, אבל פשוט רציתי לדעת עכשיו אם זה היה יכול לעזור לנו לפתור את זה בקלות יותר. כי אפשר לעשות כמו שהיה לנו במקור, בגרף של ואן דר ואלס, שזה יהיה pressure לעומת volume.
נכון.
אבל מה היה גרף נוסף שבו השווינו את השיפועים, שזה היה משהו לעומת volume.
אז היה את הנקודה שבה מצאנו את הנקודה שבה האזור הפיזיקלי מתחיל להתקיים. אז בעצם מה שאתה אומר במקרה של ואן דר ואלס זה שיש לך טמפרטורות שבהן אין מעבר פאזה ויש טמפרטורות שבהן כן קורה מעבר פאזה. אוקיי? כי כאילו בעצם יש לך משוואה אחת שמתארת את כל המערכת בכל הטמפרטורות. אז בעצם מה שמגדיר לך את המעבר הפאזה זה האזור הלא פיזיקלי הזה. ואז אפשר לדבר בעצם על השיפוי ועל מתי שאתה מתחיל לראות את מעבר הפאזה, ואז נכון אתה אומר נגזרת של P לפי V שווה ל-0 וגם נגזרת שנייה של P לפי V שווה ל-0 ובעצם מהטמפרטורה שמקיימת את זה אתה תתחיל לראות מעבר פאזה. במקרה שלנו יש לנו מקרה שונה, כי אין לנו משוואה אחת שמתארת את המערכת, אלא שתי משוואות שמתארות שתי פאזות שונות. אז בעצם אין לנו תלות בטמפרטורה של מתי להתחיל לראות את מעבר הפאזה, כי בעצם תמיד יש לנו את התיאור השונה הזה של שתי המשוואות. אז עבור כל טמפרטורה תמיד אין לנו את האזור הלא פיזיקלי הזה. אז בעצם במקרה הזה כדי למצוא, אז זה בעצם כדי למצוא מתי מתחילים לראות את מעבר הפאזה, ובניית מקסוול זה כדי למצוא את המתיחות או את הלחץ שבהם קורה מעבר הפאזה עבור טמפרטורה מסוימת. אוקיי? סליחה.
כן, הרבה מאוד.
סיימתם? כן.
אהלן.
שלום.
כן, זה משהו שקרה לי.
נראה לי כל זה. נכון?